Okay. So can you hear me clearly? Let's see. Let me adjust my mic here. Okay. So okay. I guess like to start with, we'll do a kind of quick review to look at the Venn diagram again. Let's see. So so far we have like this Venn diagram there. Like if I have like X and Y, let's say I have different colors here. Let's say this thing here is a HX, and this is HY. I probably don't have enough colors. And then like the whole thing's there, like it's a HXY here. And yeah, I'm out of color. So the thing like inside that is let me don't put it here. It's IXY, right? Then like this part here, say is a HY given X, right? And so on and so forth. So that part is a, okay, maybe I put this part. So this part would be like HX given Y. Let me turn off the just go turn off the audio on the other side. So so now if I have another variables, let's say I have another variables here. If I have this, say the whole thing, let's say H Z here. Okay, I guess I just some exercise. Maybe I don't know, like whether like you can figure that out, or like, so what's this part? Let's say, what's this part? Okay, maybe I have a question here, like very early question. Question one is like, what's this part represent in terms of this information? I guess I need to turn on the, so let me move this thing to, okay, so Anika have a question with homework 3. Okay, let's finish this review, then let's answer Anika's question. Let's wait a sec. You have to be careful, like which part is HY? Let's see, HC, yeah, that's okay. HC given Y, HX given Z. Repeat the name of these 3 circles. The 3 circles are HX, HY, and HZ. So or this I guess okay, let me yeah, Mookie have an interesting answer. Actually, it's kind of correct, but like note that we never define an IXYZ. And when you say IXY, be careful, like that is like semicolon, like between that. Because for example, like we want to say something like IXZY, so we need to specify like what does that mean? Like is there mutual information between XZ and Y, or like if you write like XZY, that will be like mutual information of like ZY and XY. So
What does semicolon and comma mean? Can you repeat that again?
Oh, okay. Basically, like for the order entropy and so on, like there's no semicolon here. Semicolon only appear for the mutual information. The mutual information is like saying what's the shared information between two variables, right? So if I have two variables here, x and y, that would be like the shared variables between x and y here will be separated by this semicolon here. But I can also ask like what's the shared information of between x, z, and y, right? So in that sense, would be like that I should have like a semicolon to separate x, z, and y. Is that clear? Or like I can say like what's the shared information between z and sorry, x and z, y. So then I should have the semicolon separate x and z and y.
In the last example, zy, you mean the combined space in the Venn diagram, zy?
Okay, this here, if you want to, okay, this may be a, you guys if want to figure out, maybe like, let's say what would be like zy and x, like what, let's say what is this value here? So this value here will be like, think of like, this will be equal to h zy minus h zy given xy. And so earlier I say like this, okay, let me how do I, maybe I should change the color and make this a little bit more readable. Let me use the so I don't, so basically let's say the red one is a hx here, right? The red one is hx, the green one is a hy, and the black one is hz here. hcy here is which one is basically this one here, right? This is hzy. And zy given x will be this part here. I'm quite out of, let's see, is there any, oh no, I guess that's as many colors I can have. Let me use blue now. hcy given x will be like this one here. Is that clear? So actually, probably I should, this one highlight as yellow instead. So then like, again, like hzy is this guy. Then hzy given x is this blue one here. So that therefore the difference, say this I xy given z here. Maybe I say ix ix. No, that's no given. Ix zy here will be this part. So is that clear for this thing here? Yeah. Okay. I yes. So now back. So is that clear? Okay. Like this.
Yes. Yes, I understood it. Thank you.
Okay. So then now back to, because many of you guys have some answers. I don't know when. Yeah. Yes, actually, the best answer will be Robert's answer. I guess like the most precise and concise answer. So and so you have this. Let's see, ICY minus IC. I'm not sure. Like probably it's not correct here. So because like you have ICY here will be let's see, where's C again? Like let me remove some of these colors I saw. See, yeah. So ICY here, this CMY, ICY here will be this part here, right? And ICX here will be yeah, this part here. So you cannot just subtract this part if this part is not equal to, so because like this part is bigger than that way. So if you want to, let me use a different color. Okay, I want to say this is ICY, right? This is ICY, and ICX is this whole thing here. You have like, you want to subtract this part instead, you have this one extra, right? So for his answer, like you want to change to something like, should be like I C I C Y minus I. So I want to subtract this part here. So this part will be like this part is actually is equal I X Z given Y, something like that. And this of course is just a chain rule. So this will be just equal to like I Y C given X, right? So and that's yeah, is that right? Let's see. Yeah, I think so. That should be wait a sec. Is that no? I'm not 100% sure honestly. So I see why this guy. Oops, so I'm sorry. Like I say something wrong. So I don't want to. Yeah, I want to subtract this part here, right? So let me backtrack this to. So forget what I just said. Like so, I said like for his answer, like I have this. Let's say this part, like I see why here. You cannot just subtract this part because this is like subtract like I X Z. So but instead you want to subtract this guy here, and this guy is generally is usually is not defined. Most people is not defined that. At least the standard textbook, like they typically don't define that. So yeah, some textbook define this I X Y Z, but it's not unanimously like used among everyone. Of course, you can define that, like define this guy is this one, then you can say, okay, yeah, then this thing here, like I mean this part, okay, I know it's like very ugly, I'm sorry. So this part here, supposedly I X, not X, yeah, I got confused myself also. I Y C given X will be equal to I Y C minus this thing, minus this thing here, minus I X Y C here. So one reason like most textbook does not define this because like yeah, I mean for example like the textbook like Mackay and also like the textbook like Kofa and Thomas, like both of them I think the only textbook I see like define something like that is like by Raymond Yuan, is a professor in Hong Kong. So but one reason I guess is like it can be quite misleading when you define something like that, because everything we have here, like what we draw here, is actually is positive. It's basically not negative. So we have like this, for example, for each of these pieces, like hx, hy, hz, and also like let's say this hx given y here is is non-negative, and also like this part, like this region here, like I y z given x, this part is non-negative. But it's not true for this thing here. So this can be like both negative or like positive. So in general, like yeah, that's one thing. Like if you want to define something like that, or like if you you write, for example, you write a kind of this Venn diagram. Oh, okay. So you didn't understand what like this can be negative.
I lost the conversation when you were saying that why is it not defined, something like that.
Oh, okay. It's not defined in the sense I would say that most textbook does not define that. This okay. I in general when okay this thing is defined like when you have like something like semicolon something, for example like this x y z, for example like this guy here, or like I have like I x z, or like I x y given z, and so on and so forth. All of these are defined, like defined in the sense like everyone in working in information theory, or like not even information theory, like in machine learning and so on, like all this like they will consider this is like something like if you write something like that, like everyone will okay, they know what is that. But for this thing, like most textbook will not define something like that, except one, maybe more. But for example, the common textbook like you have Cover Thomas, and you have Mackay, and so on and so forth like that. And I didn't track the rest, but that's one that defined this guy is by Young. But what I'm saying, like therefore, like this kind of definition, you have two semicolons saying the mutual information x, y, and z. You can of course define that as like this thing like on this Venn diagram here, but it's kind of like people don't like to define that. One reason is like this thing by itself is kind of misleading because like whenever we talk about mutual information, we talk about like and the first thing about mutual information. If you think of mutual information, it's the amount of information shared among variables x, y, right? For example, like by default here, like when I say mutual information of x and z here, that would be saying like what is the amount of information shared by this variable x and z, right? So if I define something like the x, y, z here, it's very natural to think of, okay, this will be the amount of information shared by variable x, y, and z. If you think of that way, then definitely that should be positive, right? They should be like non-negative. But that does not define, that does not actually describe something like that. This value basically just you can define that, but that is just equal to this region here, and that region will be just equal to I, for example, will be just equal to I y z minus I y z given x, right? Will be something like that, or like you can define that as like I x y minus I x y given z. But the problem, like this definition is not equivalent to saying like what's the amount of information shared by x, y, and z. There's something different. I'm honestly on top of my head, I'm not even sure like how do I describe what's the shared information between x, y, and amount for all three variables. But definitely it's not this guy. If like if that is the amount of information shared by x, y, and z, you will expect that one should be non-negative, right? But it's not. So you can say, okay, this part is this guy, but that doesn't have a nice physical meaning. So, and because of that reason, I guess most likely because of that reason, most textbook will not bother to kind of define something like that. So, and I guess I want to put this as a remark here because I guess it's very tempting first working on this information measure here. We have the tendency just write the Venn diagram here, and then okay, we will okay because I have basically this part is equal to okay, this is so bad. I'm so sorry. Let me again. Let me just erase some of this. It's like very hard to see anything now. Okay. Let me start. Just I have this is. I think I have this is red. Okay. This is green, and this is black. Right. So what I want to say is that it's very tempting to do something like, okay, I have this Venn diagram there, and I know this part is I, y, z given x, right? And I know this part is I, y, z, right? Then if I assume everything is positive, then I will just get an inequality saying that, okay, therefore, like I will just argue that I will just say I, y, z given x is less than equal to I, y, z, right? But this is wrong. Actually, we mentioned that at the beginning, because if you think of that, like this is like, okay, actually, can you think of like when is this is wrong? We kind of mentioned that, but you may not recall that. I'm not sure. Like, can you give a when I x, oh sorry, yeah, it's okay. Let me use the same thing. Let's say I y z given x is bigger than I y c. Can you give an example for that? Like when I will have like I y c given x will be bigger than I y c. Or the answer is simply equal to okay. Again, like do not use comma like in information, mutual information, because you that's confusing when you use comma in mutual information. When you say I x y z, right? You it's not clear like what do you actually mean? Do you mean like I x y c, the mutual information between x and y c, or like I x um y c? I mean the mutual information between x, y, and z. You want to separate the two parts that you want to say what share with what by the semicolon and stuff. And yeah, look at some of the answer. Like, okay, why are y or c are independent of x? So note that like your dependency should be transitive, right? Somehow like if like you have y and y independent of x, c independent of x, then y and c will be independent, right? So let's say if I have y independent of x, right? C independent of x. Yeah, can that happen? I'm thinking like, x and y depend on each other. Oh yeah. I can do that. I can do that. Yeah, I can do that. But I think that's the other way around, right? So that's not something I want. I want actually, for example, like I can have like um z is equal to fy, something like that. Then I have this situation you want, then y is independent of x, so fy is also independent of x, right? But then I have this guy is positive, right? And this is like the opposite. Like you will have like this guy, or like at least it's not this case. I am not sure like this will give you anything. It's unclear, like if just this condition is unclear, like whether this hold, it can hold or it may not hold. If there's intersection between two variables, why we assume independence? Well, seems like your question, I'm not quite sure. Like if there's an intersection, I'm not quite sure I understand the question. So if there's an intersection between variables, why we assume independence? So what do you mean by intersection? Like here?
I mean, from the Venn diagram, we can see that three variables, their information is overlapping.
Oh, okay. Like, this is like nothing to do with this diagram here.
Okay.
Yeah. I'm okay. I'm also like when you write this diagram, be careful. Like the only thing we say is that each of these thing here has to be non-negative, but they can be zero as well. So for example, like if I have this part here turns out to be zero, then this will be just independence, right? Like then
Okay.
I mean,
Okay.
like,
Yeah, that makes sense.
yeah. I guess how long is saying the same thing, but yeah, again, like yeah. So basically, like this happened. Actually, you can I think like this probably it's not clear. This several of you like make a description like that, but I guess it may or may not happen. So, but I will give a definite example that this will be true. You can just look at this way. I want this guy bigger than this guy. Then the easiest example will be, okay, how about this one is equal to zero and this one is non-zero, right? So when will this will be equal to zero will be y and z are independent, right? But I don't have like y and I don't want this to be zero. So I want y and z are not conditional independent given x. Yes, kind of like that. So what we can do is like, for example, like I can make an example like, I think I mentioned that maybe in the first class. I don't know whether I did, I forgot. So for example, I can make y, c are both like conflicting like result. Like let's say I have like y is equal to hat or tails, right? Something like head or tails, right? And C is all head or tails. So, and maybe I say even kind of digitize or like kind of like make them number, like make the output like as number. So head maybe I represent as 0, 1, and tails as 0, right? Then Y and Z are independent flip, right, of the coin. So therefore like Y and Z will be independent. But I can say like X is equal to Y plus C, right? So for example, like it's just bitwise addition, something like, so for example, like this will be, I have X, how to write that? Like X like that, I have Y and C will be like 1, 0, 0, 0, 1, 0, 1, then I will have like 0, 1, 1, 0, something like this comes up, like bitwise sum. But then if I have bitwise sum like that, like then I will have Y is also equal to X plus C, right? So then you see like actually given X here, Y and C are just function of each other, right? Like given X, then Y will be totally dependent on Z. So therefore, definitely Y and C are not conditionally independent given X. If if Y and C not conditionally independent, let's see, when Y is not independent of C or X or C or not. Yeah, I guess also is talking about the same thing, right? So if Y is not the given X, we can clearly determine Y and C. Won't that also satisfy the question? No, actually, I because I, for example, like C is not dependent on X. In this example, actually C depend on X, right? Because or at least you can say X depend on Z, right? X actually depend on Z. So X and Z are not independent. So for Muki's question, like what if X, Y, C not equal to 0, given X, we can clearly determine Y and Z. No, in general, like you have this I mean, I can have this other way, right? For example, like if these are not independent, actually I can make this independent, but these are conditionally independent, right? So okay, I guess you guys are okay with this example. Let me look at the other way around. So I don't use, yeah. I can also look at, so in general, I don't have that, but also in general, I also like don't have the other way around as well. I cannot say if Y and C are independent, then Y and C will be conditionally independent given X, say. So I can find situation that like this will be less than I, Y, Z. Wait, did I say something wrong earlier? Y, C is equal, yeah, actually this actually, I guess I probably say something wrong. So anyway, both of these cases can happen. So therefore, in general, you cannot have like say one way is bigger than one is bigger than the other. So for example, for this case here, I simply can find something like Y and C are conditional independent given X, but X and Z are, oh, sorry, this is Y and Z, yeah, but Y and Z are not independent. So for example, then the mutual information with Y, C and X are conditional. Will be 0. So just I don't know, like, is that your is a comment or question, like y and c are independent, y and z are independent, then the mutual frequency is 0, and y and x are c and x are conditionally independent. Okay. When you say something is conditionally dependent or independent, you need to say different something. You cannot just say like x and c are conditionally dependent. Right? Whenever you say conditional dependent or conditional independence, it has to be given something, right? You can say that C and X are independent by themselves, but when you say a conditional something, then you need to say given word. And C, yeah, I'm not sure like what you do you want to elaborate? I am not quite sure like what your comment. So okay, maybe like let me just get back to here. So can I think of an example for this guy? Maybe I even have this like Q3 here. This one, like how do you have example? Like I give you a hint here. It's like I want to find like this special case, like find example of like IYZ given X is less than IYZ. I would say I give you a hint that is if I can find some variable like variables so that like Y and Z are conditionally independent given X, but Y and Z are independent, then I will have. Okay, can you find example? Okay, no, the Venn diagram is not. Again, the Venn diagram, you cannot say anything from there. Again, because that things in the middle is not can be positive or negative. Unlike everything else, it has to be all like non-negative. The things in the middle, it has to be it can be either negative or positive. You cannot use the Venn diagram to prove anything. We just can't. We just proved this, right? Okay, yeah, I guess okay. I see what you mean now. So you say the Venn diagram, but when you say use the Venn diagram, you need to say that okay. Basically, what we show here is like we basically show that like this part can be negative, right? If I try to define this IXYC here, this thing like this part here, we show that this IXYC can be negative. But writing this Venn diagram doesn't guarantee that like this thing has to be, has situation that it can be positive, right? You need to first show that, okay, this one is actually can be positive. And to show that this is positive, basically that's you want to have, or like show that it can be positive, you just need to find special case example for this guy, right? So is that clear? Yes, one that is positive, but I guess like this is you're not answering the question, right? This is a tricky question, right? Like you need to first show that, like, yes, exactly. But you're just repeating that, right? But how can you give an example that actually happened? No. You I'm not sure actually. I'm not sure for what seems common. I'm not. You need to elaborate, Mookie, for your answer. I mean, like you need to. I mean, when you say going to prove that, you need to give an actual example, and you need to really show, okay, this is what, right? But that's fine. I mean, like it's okay to fall in some idea. Yeah, how long's yeah, probably is okay. Yeah, probably. Let's see. Yeah, actually, that's I think Holland's answer is it's easy. I have another under another example that maybe that I typically have like in mind, but that is an okay example also. YC equal, it may not be. It depends. If YC equal but X is independent of Y and C, then yes, yeah, you zero like you yes, that's the definition basically. So Mookie have this let's see what's that, like you say like Y is equal to C or X, something like X, but you need to say what's the distribution of X, C and X, right? You're saying C and X are independent or what? Up to may not be. If everything is equal, it will be everything will be if everything equal to X, then everything will be just the same. Basically, you will have the same node inequality. Oh wait, you're right. Yeah. If everything is the same, it's okay also. Like yeah, you're right.
100%.
Yes.
Yes, I meant to say, like the example you gave in here for XOR operation, Y equals to X XOR Z operation in here in the example. I thought that what if there is another operation like Y equals to X or Z? And in that case, if we know X, then Y and Z are independent of each other. Maybe, I'm not sure.
Oh no, but if your Y and Z independent from each other, this already will be zero, right? So this one like won't, because this has be bigger than equal to zero. So at most you'll get equality. You won't get inequality here.
Given when X is not given, then YZ is not equals to zero, right? When X is not given.
Oh, wait, but are you using the same example as we have here? Because the earlier example here, we assume Y and Z are independent, right?
No, I'm not assuming Y and Z are independent.
So, so you're saying like X is Y or Z? Yeah, actually it may or may not. I don't know. It need to check. Like, I mean, it depends on like, basically it depends on the distribution of this, right? For example, like you need to specify what's the distribution of Y and Z in that case, right? If you give an example like that. For example, like for your general example, if you just say, okay, given any Y and Z, I say that X is equal to Y or Z, then you claim that I will have this inequality here, but then I immediately I can say like, yeah, no, it's not true because I can pick Y and Z to be independent, right? So basically you need to specify when you give the conditions here, any kind of conditions here, and you say like, I want to show this guy my condition is that, then it should hold for, given your condition, it should hold for whatever things I'm going to choose, right?
Okay.
So I guess many of you have like many answer now. Yes, actually, I think like one easy thing is like, yeah, they are all the same will be, yeah, it will be simply like that. Like because when they're all the same, then this would be just equal to hy. This one would be just equal to 0 basically, because this is equal to hy given given x minus hy given x and z here. So if they are all the same, both of this will be equal to 0. So therefore, like this will be, yeah. So okay, yeah, that's good. So Alika, are you still here? Like I think like you at the beginning
Yes.
you said yes.
Yes,
Can you say like what's the question with the homework?
Yes, sir. So in homework 3,
Yes.
you said like we have 5 rainy days and with temperature 20, 21 to 25, right? 21, 23. And are we supposed to take the probabilities from homework 1?
Oh, no. You just use, no, you are not going to use anything from homework 1. It's just like the same set, kind of like same, yeah.
You mentioned in the lecture as well, the previous lecture, but how to get the probability?
Yes. You just, yeah, like in the lectures, I estimate that without the information I used earlier, so basically, like, yeah, that question is just repeating some, yeah, compute the same thing as in the lecture, but like, I want you to get the exact number to see which one is bigger, more or less. Then in the extra credit, you can actually implement that if you want to get extra credit. That's it. Yeah.
Okay.
Yeah.
Thank you.
Okay. So
And also,
yes.
sorry, one question.
Yeah.
So for the today deadline, do we have to submit some Word document or the presentation, something like that? Abstract presentation.
Oh yes. You guys have please submit your abstract. Like I think it's today or some. Yeah, I think it should be today. So you can just type it or like just you can submit Word document. That's fine. Yeah.
Okay. Thank
Otherwise,
you.
you should at least have the title and like some description what you're going to present. Yeah.
Okay. Thank you.
Yeah. So okay, I guess that's a review that took a little bit longer than I expected. That is fine. So let's see. So what I'm going to do next, I'm going to and I still have like y is not dependent on z and vice versa. Okay. Yeah, sure. What was the question?
I am typing actually.
Okay. Yeah.
I just
I'll
want to
wait
know
for you or
that.
something like, or you can just say it out. Yeah.
I think.
Someone want to talk about the presentation?
No, about this Venn diagram, I have typed this now. So
yes. It is like it's not even assumed. Like that's the same thing. So maybe I want to specify one more thing. Like maybe some of this confusion. So if you have more variables, for example, like x, y, these are symmetric. Like x, y is like hy, x. Like this the same. The order doesn't. You just think of that way also. Like and then if you have like x, y given z, w, let's say, it's the same as hy, x given w, z. Because I just think of given which one first, it doesn't change anything. So mutual information is kind of the same sign as symmetric x, y, and z will be the same as like I, z, x, y, right? But just be careful, like this won't be equal to I, x, for example, y, z. So and about for the presentation, so as I said, like okay, that's the topics. As I said like earlier, you can either just go for some of these probabilistic programming languages packages. So you can go to Wikipedia. There's actually, can you see that? Okay, I think you can see that. So yeah, for example, like you can go for packages, right? There are many packages you may talk about. For example, I guess some of you guys asked me like, is that good to talk about piano? But just like, for example, talking about Python and TensorFlow directly may not be good, but you can talk about TensorFlow probability, let's say, and you can talk about, for example, like PYMC4 or like that's why what PPL, like or like you can just go for the if you don't want to talk about packages, you can talk about like exactly information theory stuff. Like for example, Mackay's textbook like have the chapters are all quite interesting, and you can get into some of these and then just let's say the whole book. Maybe it's this one here. No, this is figure. I don't know where's the book. It's got very, very confusing. Yeah, here. You can talk about anything we didn't talk about so far, basically. So you can, for example, like from Mackay's textbook, like his chapter is quite short actually, basically. And you can, if you try to understand some of this, you can talk about that. Maybe you can select a session of them to talk about that. And yeah, basically you can talk about anything that we haven't talked about so far. Yeah, that's a plan basically. So any other concern with that?
I was thinking about the Shannon's perfect secrecy.
Yeah, I guess for the topic over. Yeah, sorry, Mookie, like,
yes,
can you repeat that? Yeah.
Yes, you just said that any topic that you haven't yet covered. So in the last lecture, you said that the topics you covered that would also be okay. So I was thinking about going for Shannon's perfect secrecy. I found the
No. I'm not quite sure. Like, no. I guess like that may not be so good. Like, yeah, I don't think like it's a good idea to cover like what we already cover. Yeah. So unless you have like really different perspective, there is something new there. Yeah. So it's saying like in a different perspective or like some other Edibles, EM, page rank. Page rank, we already talked about that. If you want to talk about EM, it's okay. If you talk about edibles, I guess it's kind of fine as well. Yeah, I guess Robert's question. I have like I didn't check how many of you like submit like just today, but a couple days ago, like I only have like a couple. I don't too worry about like too much overlap. Because it looks like there's a lot of stuff like there's a quite wide open. But if like the so I guess like that's the fortunate or unfortunate things that you speak first. Some guys like to speak later, then like they have more time to prepare. But also like if you speak later, then apparently someone else already say something like, if they say something like really nice and like really detailed, then probably it will affect like what you want to say. Something it's like same as honestly it's same as if in a conference. Sometimes like when you are in a workshop that is like in a very level areas, people talk about something like okay really up to date. I'm like sometimes you really have talks can overlap. So then like in the sense like you have to like adjust your talk a little bit, or like at least like comment like what people have talked so far, then like how I'm going to talk about something. But again, like remember, like you guys are judging you guys each other, so you don't need to please me. Basically, you should please each other, your peer, like how they will decide how good your presentation basically. So if like for example, if someone say something like very nicely, like very clear about a topic, then but I guess it's kind of difficult because I'm quite sure you will have something else to cover. For example, like even like I know Robert talk about like TF probability. Even if like someone is going to talk about TF probability, also, I think like because that thing is like quite broad there. Like I think like the first class or like first session, like the first presenter present that most likely will cover like some of the basic. Then you will have to adjust somehow. But anyway, like after today, I will post all the presentation topic there. So I guess the slight issue here is like because like everyone we have a pretty crowd session there. Like we have like basically 5 talks a day. So then I but I will basically post once I have all the topic, I will post there. So then I guess like for the same day, if you find someone like presenting the same thing and ahead of you, then you probably want to kind of like communicate with each other and to see like especially the one that present after like someone else, you want to see like what they are going to present and then like adjust a little bit. So yeah, that's but I will post like all your presentation topic like today basically. That's I honestly, if you're really I would suggest you, okay, I would suggest you actually to just go into the lecture again, like because the video lecture is available. And I'm actually, if you have a concrete question, just ask in class, or like just ask in Discord, like if you know like this Discord, a lot of activity here, but you can definitely ask question here. Sometimes I miss question, but like I'm sorry, like this one I answered so late. I guess I don't know like which one. I guess I okay asked a question, but then I didn't realize that after quite a long time. So okay, yeah, that's another question. That's new. Okay. Sorry, I did. Yeah, you can ask it. I don't know why it doesn't have a. For example, like it doesn't show the what's that called, like the notice here. Oh yeah. I'm sorry, like but I answered Alika's question now, just now. So yeah, I will try to kind of like look at this more often. Like, I'm sorry about that. Like I don't know, it's just supposed to pop up, but you can either ask question in class or then like ask question here. I think it's easy honestly, because if you, of course, if you want to go for book, there are many books about that. Like for example, like you can just go directly to, I think I have some book here. So, but I would say that it's overkill, honestly, Joe. If you just go for like, for example, Gallagher have a book like that. Let's see, like it's a draft. Let's see, random axiom. Yeah, actually, this is a quite good book. Like you can go through that. Like, for example, but I guess like the easier you can just simply ask question. I would say, because like if you are completely new to this, like I think Gallagher is a very good teacher. Like I'm very good writer as well. I didn't go with, honest. I didn't really read this, but um, I think he will. I read some of his lecture notes. It was great, so I assume it's like also like really good. So yeah, that's this one. I think, yeah. If you want to look for that, that's this one draft like. So okay, then any other questions? So if not, then I'm going back to, let's see, I need to capture this thing. So I will start, it's not exactly something new, but like you already know that, but I will just elaborate more. It's like we already mentioned, okay, we know what is entropy, right? Hx here, when this guy is discrete, it's like px, basically expectation minus log px, right? Or I can write it as a minus px log px, right? So now if this is like continuous, so if this guy is continuous, so I will have, instead of this is like the PMF, the probability mass function. So for example, if I have like x is discrete, like for example, like I have dice here, like can take 1, 2, 3, 4, 5, 6. And so I have, maybe it's totally uniform, right? Maybe not. Don't make it uniform, make it a little bit interesting. So maybe like vary a little bit. So this is like px here, let's say. This is for discrete random variable. So now if I have continuous random variable, sometimes if you look at books, they use fx, but I will use px again. So I have something continuous. So then we mentioned that like I cannot define the same way. Actually, I can still define the same way. So, but that would be like something known as this differential entropy. I mean, defining the same way, like this part is the same. I can write it as like minus log px here. But actually, if you look at the definition of this guy, is really now, if p is a if x is a continuous random variable and p is the probability density function, this probability density function. So then this sum here will instead will be an integral. So I will have px log px dx. So for example, like x should be real, right? The entire real axis here. So if like x is one dimensional, like just in the real domain. So yeah, we talk about that, but not in very detail. But continuous variable will get something like that. Now let's just go more detail on this one. So I'm think of some property here. So maybe I make it first do an exercise. So I forgot this like question 3. Maybe I don't know question 3 or question 2. I don't know. Question 3 or question 4 or something like question 4. I guess.
4.
Yeah, question 4. So let's say if I have a continuous, so this is PDF. So let's say I have a unit kind of like uniform distribution. I have x here. Let's say this width here is, let's say m. Let's say big M here. So it's a uniform. Therefore, this height is 1 over m, right? So because the area underneath this PDF is basically the probability. So probability should add up to 1. Everywhere should add up to 1. So like what is this? So what is hx for this guy? So again, I have a random variable x, have the PDF is uniform. So okay, a uniform random variable x that basically have the PDF is just this simple rectangle. Oh, don't be so fast. No, you need to compute that. It's not yeah, you cannot really, yeah, that oh, okay, that's another very fast, but I think it's kind of yes, actually that's very good. Yeah, so so what so the other is not going to give any answer? I don't know. So okay, but can't you already get the right answer? I guess look at this, is very easy, right? So I have hx is equal to expectation log px, right? So and px here is just a constant, it's just equal to 1 over m, right? So therefore it's just equal to log m. Yeah, I can log 2 base, that would be like units of bits. Okay, one thing immediately you can see is that like hx here can be positive or negative, right? It can be anything. For this entropy for the discrete random variable, like the capital H here, as we discussed like earlier, like actually just look at this again, like this has to be negative because p has to be less than 1, and this has to be bigger than equal to 0, so therefore like it should be, yeah, it has to be bigger than equal to 0. But this one, just look at this particular example here. I can have m if equal to 1, then I will have this guy is equal to 0, right? hx is equal to 0. Right? So if m is less than 1, then I will have like hx is less than 0, right? If m is bigger than 1, then I will have hx is bigger than 0. So okay, this is one big remark here. Like always remember, you have this hx can be can be negative basically. Okay, so this is for hx. Let's say look at a little bit more useful and interesting example. Let's see, I go to, actually I can just compare directly, but it's good to have the cheat sheet in front of me, or like maybe I will get the step in code in the middle. But okay, let's try. Oh, whether I should go for one more. Yeah, that's actually a nice example. Like it's short and simple. So let me give one more example. Like this, it's also on the slides here. Let's say if like t is an exponential distribution. Yes.
Can you show the
Go back? Yeah. Okay.
on that condition?
Yes.
So you mentioned when m is less than 1. Okay. So
yes.
okay, I thought it's 0. So yes, if when m is less than 1, it will be negative. Yes.
Yes. Yeah. So okay.
I was thinking that you have put the condition m is less than 0.
Oh no. Yeah. I cannot. Yeah. So
m cannot be 0, I think.
Yeah, m yeah, m is 0, then I will be infinity. That will be a delta function basically.
Yes.
Yeah. Yeah, theoretically, you can actually, as engineer, you can. That would be like just saying it's deterministic. Yeah. So T, okay. So I have, let's say, T is a random variable, is exponentially distributed with lambda. So this is a, for exponential distribution, like PT here, the PDF is given by, let's see, is equal to lambda exponential minus lambda T. So it's something like that. If you remember exponential distribution is something, oops, it cannot go to zero, but it's decay like that. So it's like the variable can only be positive. So right, this side is like nothing there. On the negative side, there's nothing there. So the PDF something like that. So again, maybe I won't ask you to do exercise for this one. So should I? Or honestly, I don't know. Maybe that's not because you guys are so quick anyway. This will be like question 5, let's say. So what was HT in this case? Like PT is this one. Oh, by the way, let me make you guys easier. Know that, like, I will just give you one thing, that expectation of T is equal to 1 over lambda. So this will make it easier. Let's say if I have a distribution like that, the mean is given by 1 over lambda. Oh, that's quick. That's nice. Yeah. And yeah, I guess I it's okay. Like that's correct. Basically, it's very easy, right? You have like expectation again minus log PT, right? PT is this guy here. So it's a equal to expectation minus log lambda minus lambda T here. So it's equal to expectation minus log lambda minus log exponential minus lambda T will be minus lambda T coming up, right? So then like this would be just equal to, this is just a constant now, so it's just minus log lambda, and this would be plus lambda T. So plus lambda expectation T, as I said, this is just equal to 1 minus lambda, 1 over lambda. So therefore it's just equal to 1 minus log lambda. So okay, so this is a exponential distribution. Yes. yeah, it's quick. So yeah, I don't know. So you guys can put in there, like if you're still around, I don't mind. Yeah. So and just show that you guys are actually listening. I'm here. So let's see. Look at the let's px. So let's say I have now I have Gaussian distribution. So I guess sometimes I don't remember exponential distribution. I know it's exponential. I can figure that out because I know it's exponential. I should integrate. If I don't remember the constant, I know that integrate that PDF should be get me 1, but I may not remember this form exactly. But I think like try to remember Gaussian because Gaussian is so common and so important. So let's say it's Gaussian. I have like, let's say X is Gaussian. Let's say I pick mean. Actually, I can make zero mean, but let's say I have a mean mu. Because know that like just like in no, actually you use here I can use lateral log or like log base 2. It doesn't really matter. If I use yeah, you're right. Actually, here I assume natural log because otherwise yeah. Actually, this is good. You catch me. So I have this. Therefore, is I'm doing natural log here. So I'm doing natural log. Therefore, this unit is actually lat here. Yeah. So you caught me. Yeah. So of course, if I'm not doing lateral log, then I will just basically it's also equal to log 2, something like log 2 1 minus log lambda bits, something like that probably. It'll be just like different by a scaling factor. Just like you're measuring something like in terms of inch instead of a centimeter. So that would be like just a factor by 2 point something. So if you use net instead of base, it's basically just differ by like log 2. I forgot log 2 to multiply here, like multiply here. I forgot, but it doesn't matter. Yeah, you can figure that out. I say it doesn't matter because for stuffs you can figure that out in 2 minutes, then I don't bother too much, right? I guess that you can be the same as well. So, but if like stuff that you don't really understand, that means that you cannot figure that out in 2 minutes, then probably like you should kind of pay attention to that. So, okay, back to this Gaussian example. I have something is Gaussian. Okay, I guess it's good to take a break, and then I would just make this as the exercise, I guess. So if it's Gaussian, then the Gaussian distribution, you may not remember that, but actually it's good to remember that. The PDF is given by, at least you should know the exponent. The exponent is a x minus mu square over sigma square to sigma square. So it's like you have mean somewhere here, right? So let's say this is mean mu here. So, and as you deviate from the mean there, you will decay, right? You have a bell-shaped decay, something like that. And if your variance is bigger, then like you will spread like wider. So it's over like this sigma square here. And there's a scaling factor, normalization factor is like 2 pi sigma square, square root of 2 pi sigma square. Now maybe this is Q6 here. Then I guess you can work on that during the break, maybe like maybe we'll come back like 4:30. So this is like what's the HX basically. Okay. Oh, actually, I still have 1 minute. Okay, I guess let's come back to this. Like this is not very difficult. It's like what we have here. You don't actually need to do integration or something like that. It's good to know that the PDF is like this. And for this PDF, we know this is the mu, this is the variance, right, for the distribution. So therefore, I know that expectation x is equal to mu, and expectation like x minus mu square is equal to variance, let's say. I don't actually need that, but this is good to know. Then I have this the hx there. It's just a expectation of this minus log PDF. So it's equal to expectation minus log this thing is just log 2 pi sigma square. And okay, this time I'm careful, like say log base e. So then let's say in terms of bits, then log this part here, so I have minus x minus, actually this would be plus as well, because I have minus sign here, mu square over 2 sigma square. And then I have log e here, something like that, I think, right? So then I will have this thing here just constant. I have like log 2 pi sigma square. Then here I will have expectation. This is a bunch of constant here plus log e over 2 sigma square. Actually, I need that. Expectation x minus mu square. That is simply is equal to variance is equal to sigma square, right? So therefore, I will have log this thing. Let me write 1/2 2 pi sigma square plus 1/2 this sigma square got cancelled, like this two got cancelled. So 1/2 log e. So therefore, it's like 1/2 log 2 pi e sigma square. So that's for Gaussian, for unit Gaussian, univariate Gaussian. Okay, I'm thinking whether I should go to the multivariate Gaussian. It's good to know multivariate Gaussian. So basically, you have a multivariate Gaussian. For example, if a 2D, let's say I have both x and y here, right? So I can think of like a vector x is like basically x and y, like two variables. I'm split. I have a Gaussian, for example, like I have the mean is somewhere here. Right? I have the basically if I sample that distribution, I have like got samples like this, right? And this more or less I have the variance, like the variance itself will be kind of will be a matrix here. So actually it's known as the covariance matrix. And the PDF in this case will be, again, I just remember the exponent. The exponent will be exponential minus, it's very similar, minus 1/2. I have like x minus the mean, mu, right? Let me make a vector as well. So if I have a scalar, it will be like square or something over like sigma square, right? So, but here instead I will, because it's a matrix, I will have like this is a vector multiplied by a matrix. I have a covariance matrix, it's like sigma, why is sigma? Sigma inverse x minus mu. So let's see, this is transpose. So here it's like x and mu are column vector. So I have this a column vector, this is a row vector. So this thing multiplied by this matrix here will give you just a scalar number. I want a scalar number because I have this is a probability, right? The probability have to be a scalar. So this is the exponent, and then like the normalization factor, I think is like what's that? I forgot actually. Not it's equal to, again, the square root, but it's a determinant 2 pi sigma. So that's the PDF basically, px. So any question for that? This is like for multivariate Gaussian. So the PDF for multivariate Gaussian, and we can do the same thing. Okay, find the coherence matrix for this guy. It's a little bit trickier, but it's like the same thing. I will. It doesn't necessary to be diagonal. So if it's diagonal, then you have x and y independent, basically, actually. The coherence matrix is really, you can think of the coherence matrix like it should be the ij element of the coherence matrix will be the expectation of xi minus mu I and times xj minus mu j, something like that. So of course, if I kind of like degenerate back to the scalar case, then this will be just equal to the variance, right? So I and j are the same, and then like will be like just a variance. Yeah, here like as Vishnu said, like there, like if I assume like x is I have dimension n there, then there's no bar underneath. If I dimension n there, then like the size of this sigma here will be n by n. So and if you think of like, okay, in general, when I is not equal to j, then it's really the this is like sigma ij. This guy here is the I'm 100% sure. This is like called the correlation coefficient, something like similar to that. Correlation coefficient of the two variables, basically, xi minus j. And so for yeah, that's actually that the Gaussian, you can think of the multivariate Gaussian in high dimensional space is like just a football, like American football, like somewhere in the high dimensional space. And you have a mean in the center, and then you have like ellipsoid shape, like as it spread out. It can be oriented like in different orientation, right? But when you have this football, it's like aligned to the axis, then basically like everything will be independent. I mean, the variables themselves will be independent. For example, like I spread this thing like this is like distributed like this way. But if it turns out it distributed like aligned with the axis here, then the components like for each of the direction will be independent. Yeah, it will kind of like will be elaborate quite far if we want to show that, but it's not difficult to show actually. You can go back home and try to think about it why so, because in that case this would be diagonal. So if we have the coherence matrix basically will be diagonal, and so then yeah, actually, then when this is diagonal, then you will can this thing here can be just written as a sum of something like xi minus mu I sigma I square inverse, where sigma I square is equal to sigma I. I need the 1/2. I don't know this. Yeah, let me just write. when your sigma is diagonalized, can be diagonalized, then it becomes something like that, right? So when it becomes something like that, then this, I'm sorry, like this probably is like very hard to read, like exponential, that exponent may be something like that. But this exponent like that, I can just change it as a product, right? It would become like exponential something product like I1 to n. Then of course, then each of these variable like xi here will be independent. So, but okay. But anyway, that's some intuition about this multivariate Gaussian. Now let's try to find the differential entropy of x here, the vector x here. So I have like hx here would be what? Is equal to, again, it's just exponential minus log p x here. But px is given by this guy. I have, I don't know, that's a lot of writing. I guess I'll just say show the slides this time. Okay, this oh, okay, maybe I shouldn't use reference. I cannot write on that. Okay, let me first go to that page. Let's see, this is what, 30. Okay, so I have something like that, right? So basically, I have again like expectation minus log px, and then px is simply this thing, right? The whole thing, and then I take log of this guy here. Then if I take log of this guy, then I can split the log here. So I have log this guy, it's just a constant, I put it out, and log of this guy, log e coming up, right? And then I have the remaining part, I have 1/2 here also, but I have this thing here. Now this guy, like, it's just a product of like a vector, right? A row vector with a matrix with a column vector, right? So I can just write that as a summation, right? So it's a summation of I and j here, right? Summation. So basically, I have, yeah, I don't know how to explain that. Like, do you have any question of that? This is like simply expanding this product of like matrices with like summation. So, and now, but when I do that, like then each of these guys is just a scalar, right? Then I can pull this out now, pull, or at least I pull ahead of that, right? So then I pull ahead of that, I have like sigma inverse, the ij element, sigma inverse. And this guy, I have this one here. But remember what is this? This is actually just equal to sigma ij, right? So I have the sigma ij inverse, sigma ij. So then these two just got, just got like cancelled, right? Essentially. So this got cancelled. This sum ij will be sum over 1 to n, right? Yeah, so this is just equal to 1 here. And I will have, wait a sec. Okay. I need to be careful. So yeah, sorry about that. So when I'm here, this is equal to sigma algebra is also equal to sigma ji. Then I can write this as sum over I, then sum over j, right? So I will sum over j sigma I sigma inverse the ij element product like sigma j I element. But what's this thing here? This is just equal to, let's say this is matrix A, this is matrix B here, right? This is like A ij element multiplied by bj I element, sum over j. This thing will be just equal to the A, B, the I elements, right? So therefore, like this guy here will be just equal to sum over the I. Let's see. This is yeah. This product here will be just equal to sigma inverse multiplied by sigma, and look at the I element of that. Sigma inverse multiplied by sigma is just the identity. The I element there will be just equal to 1, right? So therefore, like this whole thing, therefore, is actually just equal to 1, right? So then I sum I equal to 1 to n, sum over 1, this thing here, the whole thing here will just give me n, basically. So therefore, like I will just have like this is equal to n, I put n here, so I have this here. So the final expression is like, that is pretty nice, actually. 2 pi sigma like e to the n. Actually, because this sigma is n by n, this matrix here is n by n. So this thing here is n by n. So note that if I have a determinant a n a here, okay, let's do a b here. Let's say this is matrix n by n, and this is multiplied by a here. The determinant of this guy is equal to a to the n determinant of b. So you can easily verify that. So therefore, like if I have this thing get into this guy here, actually I can make it even better looking. It would be like the log determinant 2 pi e sigma, something like, and take the square root of that. So that's just the entropy for the multivariate Gaussian. So okay, let me use back to my tab. Okay, one last thing, not last thing, but one thing, yeah. 2 pi. Actually, if you get 2 pi, pull it out with the other way around, you do 2. Yeah, you can do that, but it doesn't look good, right? It looks nicer, I guess. You can pull it out, would be like 2 pi. Yeah, you can get like 2 pi e to the power n determinant sigma. Yeah, you can do that also, like, yeah. Yeah, you can do the log. Yeah, there's a log here. Yeah, yes, and I can put that 1/2 also here. Like, yeah, it depends on what you want to write. Like, yeah, that you can write like this also. Just like for my case, I like this. It seems like easier for me to remember. Like, I have this determinant and 2 pi e and sigma all inside. Yeah. Log determine trace. Yes, I guess you may wait. Oh, I can't do, yeah, I guess that one you need to have the log is not defined there, right? There's a log matrix. I don't know. Of course you can do Taylor series expansion for that. Yeah, I don't know. You may try to show that. It may or may not. I'm not 100% sure. Yeah. So anyway, like so okay, one thing, like, well, I don't know, I say last thing to talk about the Gaussian is Gaussian is important as you know the central limit theorem, and also another importance you can see why why Gaussian is important in terms of information theory is that like when you have like a fixed variance, let's say you consider any distribution, like if I have a distribution px here, if I fix the variance, let's say the variance given is like sigma square, then you look at any distribution, the distribution give you the highest entropy will be Gaussian. So basically, if x, let's say if this is x here, right? X have a PDF, I don't know what's the PDF, but it turns out the variance of x, let's say, variance of x is equal to sigma square, let's say. Then I already immediately I will know that hx will be less than equal 1/2 log 2 pi e sigma square. That's basically the entropy, as we discussed earlier. That is basically entropy of, for example, Z, where Z is some pseudo mean Gaussian with variance sigma square. And let's show that. So Gaussian, that's basically, it's like a lemma or something, that Gaussian maximize entropy for fixed variance. So proof is quite simple. So let's see if I have let's see if I have let's say, oh yeah, I use that, like I have x here, right? I have c here, let's say. So let me look at the consider the conditional, not conditional, I'm sorry, the KL divergence between p x and let's say Gaussian. Let's say, how do I write that? Let me write like that, like normal 6 sigma square x, right? Maybe I put even a mu here, it doesn't matter. Pseudo mean sigma square. So the KL divergence between like this guy and this guy. Of course, I noticed the KL divergence has to be bigger than equal to 0, right? And this is like just any distribution with the variance is equal to sigma square. Then this guy, the KL divergence will be equal to px log p. Oh, actually, by the way, I didn't show that like the KL divergence for continuous distribution. 6 square. Oh, sorry. This is a sigma square. Yeah. Just the variance is the same. Like the variance of this guy is the same as the Gaussian distribution. Yeah. And the KL divergence, yeah. I mean, I didn't mention that like px and qx here has to be bigger than equal to 0. Let's see. And also like the same thing, like it will be equal to 0 only if and only if like you have, basically you can go back to that proof, like and anything we do in that proof, like it just hold, it doesn't matter whether it's like continuous or discrete. So therefore like it's basically, you still have like Carroll divergence whenever like you have two distribution, consider any two distribution when they are not the same, then the Carroll divergence should be bigger than equal to bigger than 0, and when they are the same, then the Carroll divergence will be equal to 0. So then I have the Carroll divergence between this and this will be equal to, I guess I just make shorthand, just nx, right? This nx dx, something like that, right? Then it will be equal to integral, I can write minus px log px. Oops, why am I writing? Yeah, log px dx, right? And plus px log and x. I guess I should put minus here. Minus plus minus. Let me write it this way. Oops. So I'm out of space. I write like this because then this is just the entropy, right? The entropy for P. So this is just equal to hx, right? This is just equal to hx. So this is minus hx. And this guy here, okay, this guy, know that like what I have here, this is log, this whatever, this thing here. And the PDF of this guy, I have the PDF, if you remember, it doesn't matter actually. The PDF is actually, I think it's maybe I write, how do I write that? Actually, it's good to even write that mu sigma here, mu sigma square here, dx. Right. My point is like this guy is nothing but it's equal to expectation minus log and x mu sigma square. But I need to be careful. Like my expectation here, say apply to the distribution P here. If I apply to the distribution like N here, that will be just give me the entropy of the Gaussian distribution. But this is expected on like P here. But note that like when I look at this guy here, that PDF of N only depend on mu m sigma square, right? So therefore, whatever this thing here will be just a function of mu m sigma, basically, mu m sigma square. And this function, like if you think of like this is a function of mu m sigma square, expectation of this mu in terms of function of mu m sigma square, this thing will be the same. This is an expected of P in terms of P, will be the same as an expectation of N, right? In terms of the Gaussian. Because the mean and the, here I didn't specify the mean to be the same, just assume the mean to be the same. So because the mean and the variance are the same for the N and the P, right? So therefore, like I can just have this expectation, original expectation in terms of P. Now I argue again, let me repeat the argument again. Like I argue that this is a function of mu and sigma alone, right? So therefore, like when I do the expectation, actually I didn't write it quite nicely. Actually, after I do the expectation, that mu should be disappear. But what I want to say, like this is, you can maybe this is a function of mu and sigma square. Yeah, it's only a function of mu and sigma square, actually, mu and sigma square, right? Because it does not depend on x really. And then like, because it's only a function of mu and sigma square, and for both distribution, like P and also the Gaussian distribution, it have the same mu and sigma square. So therefore, like this guy here is actually just equal to doing the same thing minus log n x mu sigma square. Yeah, of course you can show that, like write down everything, but like you can just, I mean, you can do all the steps, like just yourself to find that they are actually the same. But just knowing that like this thing, this expectation over x is nothing, but it's actually just a function of mu and sigma square, and both of the distributions share the same mu and sigma square. Therefore, like these two expectations have to be the same. But then like when I write the expectation of this guy here, now then this is nothing, but it's just the entropy of the Gaussian distribution, right? Therefore, this is just equal to h and x, let's say. Let me write it this way, right? So then I will have like h and x minus hx is bigger than equal to 0. Therefore, like h and x is bigger than equal to hx. So again, like, it means that it's like for any distribution, for the fixed variance, you will always have the distribution have the largest entropy when the distribution is like look like a Gaussian. For example, like if I have some distribution like that, if it turns out the variance is equal to this, now I draw the same distribution, not same series, sorry, a Gaussian distribution with the same variance, then this distribution will have like larger entropy than this one. So is that clear? I'm not going to the proof for, actually, because I honestly, this proof here for I'm showing this a scalar, what is it? Actually, this argument here hold even when you are going to multivariate Gaussian, because when you are multivariate Gaussian, then this thing will be not a function of mean and variance, but a function of the, yeah, still the mean, but it's a covariance matrix. And again, we can make the same argument that like this thing here is a function of mean and covariance matrix. And because for this Gaussian distribution also have the same mean and covariance for the same Gaussian, for Gaussian distribution also have the same covariance and mean, then these two values will be the same. Then eventually we still have like terms like that, like the first term will be just entropy of that original distribution, and the second term I can argue that this is actually the same as the entropy of a Gaussian distribution. So therefore still we will have like, even when you have the variable is multivariate, it's not just one dimension, but it's a high dimension, we still have like multivariate Gaussian will have the highest entropy. So it's a little bit mouthful, but this is basically the key step. So if you if you have any doubt, of course you can just elaborate this, and then you will see like why it's so. But yeah, and that's for the Gaussian, and so that's actually why like we always see Gaussian distribution, right? If you think of it in the lateral world, because you have the second law of thermodynamics, basically the entropy has to keep increasing. So if you think of a distribution, they start with something. No, the energy is basically like the energy is more or less is proportional to the variance of that whatever signal, right? So the energy is not going to change if you're in a closed system; it's still the same. But then as entropy has to continue to become bigger and bigger, the only way you can get a bigger entropy is that you get the distribution of that whatever physical phenomenon to become more and more Gaussian. So therefore, like, yeah, if you put things like in a closed system, eventually everything will become Gaussian. Yeah. So, and that's why like study Gaussian is so important, right? Because yeah, they will just naturally appear. Yeah. So any question for that? So one more thing. So let's try to link let's say the differential entropy with the regular entropy, the discrete entropy. Let's say if I have like some continuous random variable like x here. Now maybe it's Gaussian. I can assume this is Gaussian, zero mean Gaussian. Let's say, and let's say I'm going to discretize that. So I have something like, for example, you can consider this as like the height of the students in the class. And then I discretize that into like in terms of like centimeters or something like that, like in terms of like to the, well, how do we call that? Like with no decimal places, just in terms of like centimeters. Then so I have let's say I have a quantized version. I call it x delta. Let's say maybe I'll put a delta somewhere here. So this is a quantization step here. I just quantize that. So now after I quantize that, this will be a discrete random variable, right? So this is discrete, so therefore I can talk about the regular entropy, right? I can talk about x delta. And x delta, x delta, so therefore it will be just something like equal to px delta log px delta, right? Something like that. I have a minus sign here. And I can approximate this summation into an integral, right? So I have the px delta is what? Px delta is approximately equal to the original px times, let's say, the delta, right? So that's the probability of that. I sum over, this is sum over x here, log p x delta. So I have px delta is approximately, again, I can approximate that, right? So then this log here will become what? I can split the log here. I will have log, I will have minus x px delta log px here, right? Minus x px delta log delta here. Right? So anyway, this part here, okay, this is a constant. I can put it out. And this whole thing here, this px delta here, as I actually, again, I can just approximate this back to px delta. And anyway, this whole thing just sum up to 1, right? Because it's just summing over all the probability, possible, sum over the probability of all the possible situations there. So therefore, this is just sum up to 1. If I put it out, this just give me minus log delta, right? And this thing here, I can approximate that as an integral. That would be like px, the delta here become dx there, log px, right? So then this is nothing but just the differential entropy, right? So now therefore I can connect the differential entropy with the regular entropy. Think of like if I going to, if I have delta is sufficiently small, then it's a good approximation, something like. So this, of course, this is approximate. The approximation is starting from somewhere, yeah, approximation somewhere here, yeah. So maybe I just write here again. Hx delta is equal to approximate hx minus log delta. So we can use this to approximate things. For example, like I can make a question, like I don't know what is this question. What question? Anyone have idea? 5 or 6 or? Let me see. 7. Okay. Question 7. Let's say, I do this Gaussian distribution. Let's say like I have students' height, like the mean is like 135 centimeter. I don't know. Let's say the height of some students. I use H again. Maybe I just I just call it X again. Like this is like maybe mean 175, and then like the variance maybe 10 centimeter. I don't know. That will be square. Maybe the standard deviation is 5, then 5 square. So the sigma is equal to 5. So if I'm going to, let's say I have like 100 students here, and let's say I want to have 1 decimal places. Let's say that means that I'm going to delta is equal to 0.1, something like for example, if like 165.19 centimeter, I will just change that to 165.2 centimeter. Let's say 175 seems a little bit tall. We have girls as well, I guess. Maybe. Yeah. So how many bits need to store the heights of all students? So they could, I mean, this is like 100 students, all 100 students. So is that clear, the question?
Can you repeat this once?
Yes. So the question is like, I have 100 students here. Their height is like normal distributed, and the mean is 170, and then the variance is like 5 squared. So I mean the standard deviation is like 5. The sigma is equal to 5. Now I want to store all these numbers in a file, let's say. I don't know what kind of compression you're going to do. So, and the position I want to store is up to 1 decimal place. So therefore, like the delta is equal to 0.1. So the question is, I want to store all 100 students, the height of all 100 students. How many bits are needed? So in theory, how many bits are needed? That would be like basically the entropy. How many bits are needed to store all these height, the numbers of this, the height number of these students. Wow, okay. You need some calculation. Okay, this is not. Did you compute that? Is that so quick? I don't know. Like, okay. Yeah, maybe you're. Yeah. I don't. I didn't really. Let's see. I really may need to pull up a calculator. So any others have like the so oh, that one is a Yeah, I guess I saw your numbers. I almost forgot also. Like, yeah, our question asked like, what's the total number of bits needed? Yeah. So you need to basically need just using this way. It's so maybe I'll just quickly go through that. Uh, so so it's actually quite simple. So I have the per student the entropy is like just equal to that way. So it'd be like hx is equal 1/2 log 2 pi e sigma square, right? Something like that. And minus log delta, that's in terms of bits. Oh, know that like most of you guys I forgot to, besides Kanju, I guess, like you have to multiply to the total because like, the question is asking like what's how what's the how many bits are needed to store the height of all students, right? So I'm 100 students. So per student, like that would be the number of bits needed, right? So like if I have 100 students, 100 times of that. And log delta here, I think is a this is 0.1 here, minus log delta, I think it's like 3.32, something like that, or 3.3219. And this one here, if I compute correctly, is a 4.369. So if I have 100 of them, I add together, it's a 7, 6, 9, 10, something like that. Yeah, so about like 700, like, yeah. So yeah, about 700 bits you need, like 760, 70 bits needed to store all this information. So okay, this is all I kind of like to talk about for differential entropy. So okay, next thing, like I originally thinking like maybe yes, log is base 2. I use base 2. Yeah, base 2 is usually better, like because you want to tell people like this is number of bits. As I said, like actually if you look log base E, it's just like get a different unit, like that's all units called nets. And I don't think most people use that now. So and of course it's just only differ by a constant. I mean by a scaling factor. And so okay, what I'm going to do next is I want to just talk a bit of channel capacity. So I won't go very elaborate as I usually do, because I guess the nature of this course is different now. But I guess it's probably I have a name like information theory in the course title. It probably should still like at least talk a little bit about the channel capacity, because it's traditionally this is a must-have like topic like inside information theory. So if you study some communications before, like of course you heard of channel, and in terms of information theory, it's very general when you talk about channel. Channel is basically you think of like anything you have information like coming. Let's say like you have some input coming in like X, then it you can, from this other end of the channel, you can get some output y. This y, of course, should depend on x somehow. If it's totally independent, then the channel will have, you cannot send anything through the channel. And the goal is, of course, I want to send some information. So typically, I have a channel here, right? I have like an encoder that I have some message here. I'm going to encode this message into some actually stream of like code word that I'm going to send through this channel. Then at the other hand, I'm going to receive this stream of I don't know, distorted, usually noisy signal back. Then I'm going to decode back. Then I get the message back, like M hat here. So in terms of information theory, we don't care about like how you're going to achieve or like how you're going to do this encoding and decoding like in practice. But what we're interested in is like if you have some description, some characteristic of this channel, then how much information we can actually pass through this channel. And the channel will be, let's say, will be kind of completely characterized by simply the conditional probability, right? So given your input x, what will be sending out from, I mean, what will be the other end, like will be like what, how will be the output like distributed? So as long as I'm given this, what's the information theory said is actually the capacity is very simple. The capacity will be simply just equal to Ixy. So if I have the distribution or the random variable x will be like given, okay, the input is like given by a random variable x here, the output like given by a random variable y here. Of course, y will kind of depend on x based on the channel characteristic here, right? Then the amount of information I can send through this channel is simply Ixy. And of course, I can adjust the distribution of x here, right? I can modify the distribution of x here somehow. So what I want is that I want to maximize the distribution. Also, I should say maximize the mutual information for adjusting the distribution of the input. And so the capacity is simply equal to that. So is that clear? Any question? Intuitive wise, it's actually very simple, extremely simple. Of course, we need to prove that. Basically, the proof will be saying, okay, can we find a scheme that we can send message at the capacity, basically? So basically, we have a forward proof. It's like will be find scheme such that we can send at the rate, oops, of the capacity, right? And for the converse proof, okay, I probably won't talk about the converse proof. Actually, the converse proof is very similar to what we talk about the source coding theorem. We also give a converse proof there for, yeah, you will probably need to go back to earlier lecture. Like in the past, I will talk about the converse proof, but this time I guess I will skip that to save time. That's basically use the Fano's inequality, if you remember, like somewhere we talk about the Fano's inequality. So, and the converse proof will be like if you have sending, like if weight is larger than the capacity, then probability of error will be always bigger than zero. It will be always non-zero. So you cannot send message losslessly. Did I emphasize losslessly here? I guess I didn't. So I need to make sure that M hat is equal to M. So the probability of error is equal to zero. So this is actually probability of error. Right? M hat is not equal to M. That probability will be equal to zero. Again, if you send below the capacity is equal to this guy here, you can always you can find a scheme. Maybe if you find bad scheme or like stable scheme, you may have probability of error, you have probability of error is non-zero, but it's possible to find a good scheme such that like the probability of error is equal to 0. But on the other hand, if your weight of sending through the channel is larger than the capacity, no matter what you do, the probability of error will be bigger than 0. So is that all clear? So I will give a sketch proof for this thing here. So before that, maybe I just go for some, yeah. Maximize, we want to maximize. Because like you want to send as much as possible, right? This is something you can adjust. So this is like given by the problem, you cannot control the channel, but you can change X, right? So basically, if you think of IXY, it will only depend on Px and Py given X, right? Because if you have given Px, you have the distribution of X here. If you have like both Px and Py given X, you have the distribution of Y there also, right? Actually, you have like both X and Y at the same time. So therefore, like this will specify the IXY completely. And this part is given by the problem. You cannot change that. That basically is how the channel behave. But this part you can modify that, right? You want to change whatever. And you want to change in the sense that you just will be able to send as much as possible. So therefore you want to maximize. Wait. You say it's the capital maxima IXY or IX? I didn't read your question clearly. Maxima IXY or IX small y. It's a big IXY. So this actually I small xy probably does not make sense because yeah, actually when we talk about like mutual information, entropy and so on, yeah. So you say maximize or mass of I, yeah, it's the same thing. Okay, like this engineering guy, like when we say maximize, it's the same of max. Or sometimes people say supremum of that, like, but I guess it doesn't matter. It's only we care about analysis, like when this thing is not, you know, like it's open and so on, like, yeah. But yeah, it doesn't matter. Like I assume this thing, like this function is closed, so I always the maximum is, yeah. Yes, the maximum value is the cap. Yes, the maximum value is the capacity. Yes. Because like that will be the maximum amount of information you can send through this channel. So per channel use, by the way, is per channel use. So of course you can, if you use the channel more times, you can send more information, right? But on average, per channel use, you can at most send like IXY through this channel. That's a very intuitive, actually very reasonable, right? So IXY is the amount of information shared between X and Y. And you cannot send more information than that shared information there. So let me give an example. First, let's say this so-called binary symmetric channel. I guess everyone heard of that. That is I have the let's see, can it be HX? No. You mean instead of maximizing ISY, just maximize HX or? Oh, okay. Remember that the thing is like we want to have the information actually sent through the channel. So therefore, it's important that what you after you send through, like you are able to recover that. So if I just try to maximize HX, I can send whatever, like how much I want. But the problem is that at the other end, I am not able to recover the message. Then it doesn't do anything. And so. Oh yeah. If okay, if your py given x is equal to 1, let's say something like that, then it's saying that like this is deterministic, right? So if I have something is 1 here, I am assuming that this is a discrete random variable here. Wait a sec. Okay, depends on how you define that. But let's say if like, let me don't write this, but let's say if y equal to x, then your ixy will be just equal to hx, right? So, but then in that case, your channel is like trivial, or like it's like yeah, because the channel itself doesn't really yeah, there doesn't have any noise there basically. It's perfect channel, so it's basically not there, kind of. Whenever we think of channel, it's always the channel is like have some defect there, have some noise there. Yeah, so therefore, like in general, we don't expect y is equal to x directly, but instead like y will be some kind of noisy version of x. So let's say the binary symmetric channel here, consider this binary symmetric channel. I have basically it's binary as the name suggests. So both x and y is binary. So it would be something like that. I have x coming in, so it can get me x if equal to 0, but I have like non-zero probability that I will get y is equal to fifth of that. So I will have probability p that like x is equal to 0, but y is equal to 1. In the same token, like p probability that like I have x equal to 1, but y equal to 0. So this is like symmetric because like this for both like input, like when x equal to 0 and like 0 or 1, the kind of like crossover probability, because this crossover probability is equal. And for the capacity for this channel here will be something like just ixy, like this. Right? Let me erase this to get some space here. Maxima over px here, right? Then this guy will be equal to, let's see, equal to hy minus hy given x, right? Maximize px, right? And hy given x is what? It will be like hy. Actually, hy given x is equal what? Maybe really quick. I don't know what question is it, Q8 or something like that. What's hy given x? For this channel, no. I have like okay, again, like for the binary symmetric channel here, y probability y equal to 0 given x equal to 1 is equal to p, y equal to 1 given x equal to 0 is equal to p, something like the crossover probability is equal to p. Yes, what's that value? Yeah. Yeah, that's okay. Yes. So anyone get the can you write that, like if I give that the crossover probability is p, so I'm not sure how many people are still around. So and So, but the question is like, it's clear, right? I guess maximum would be 1 bit, but if I have this crossover probability exactly P here, so that means that like my HY equal to 0 given X equal to 1 and PY given PY equal to 1 given X equal to 0 equal to P. So given this, the other probability is also known, right? This other one is 1 minus P and 1 minus P here, right? So in terms of P, what is this? What is this in terms of P? It's a good guess, but not quite right. Not right. So yeah, you probably want to go back to that basic. Yes, this is actually pretty close, but I guess you miss a little bit. It looks probably not white. So let's do it together. So at least like what was I mean the first equation is correct, right? I have like HY given XP X equal to 0 plus HY given XP probably X equal to 1, right? The point is okay, I have to say this. HY given X equal to 0, right? This plus HY given X equal to 1, right? And so what are this guy here now? Yeah, so almost correct. So yes, and this is just HP, right? These two guys are just HP, but you have to be careful. So Y given X equal to 0, then given X equal to 0, what's the distribution of Y? The distribution of Y is just P and 1 minus P, right? Basically, I'm here, right? X equal to 0, I have the distribution of Y is just 1 minus P and P, right? So therefore, like this is actually just equal to HP 1 minus P, right? Or I can write shorthand, it's just HP here, right? And also like this guy is the same, it's also HP here, probability X equal to 1, right? Now, okay, you guys have to be careful. The HP here, I can pull that out is probability X equal to 0 plus probability X equal to 1, right? That's sum up to 1, right? So therefore, like this thing here is actually just equal to HP. Yes. So yeah, this value is just equal to HP, right? Oh, and by the way, you guys want to use big H here because it's here is the discrete case. You want to use the capital H here because it's a binary discrete channel, binary symmetric channel. The variable is yeah. So now okay then. So therefore, like this things is just equal to HP, right? This is just equal to HP. Now, and this guy here. So therefore, this actually does not depend on, does not depends on px, right? This is like p is just given by the channel itself. This does not depend on px. It's equal to so maximums px here, right? Okay. Anyway, just ask this maybe I'm not sure. It's last question. So what will be what will be this then? Like what's the? Can you find the capacity now? Like I given this is HP. Now what should be the capacity now? Capacity is equal to maximizing IXY, right? For given P with respect to PX. And as I said, like, I can split into HY minus HY given X here. And then I say HY given X is nothing, but it's just equal to HP here. Now, what's the last step now? So what was this exactly? How many bits there? The final question is like, what was the maximum value of this guy basically with respect to P? That's weird. So okay, your capacity, where is that? I'm expecting a solution that does not depend on, it will be only depend on P, right? Because the capacity should only depend on P, right? The whole question here, the only parameter we have is just P, small p here, and nothing else. So we expect that the entire channel is characterized by this P here, and the capacity should only depend on this parameter P and nothing else. Note that you have control of X, control of like distribution of X. So you have control of distribution of X. That means that you also have control of distribution of Y, right? Because you have PXY is equal to this guy here, right? Is equal to this guy here. This thing is controlled by your problem is controlled by P here, but this thing you have the freedom to just modify that, right? You actually want to modify in such a way this capacity is maximized, right? Or actually this expression is maximized. So what should I pick for PX such that like this will be maximized? And what will be the value basically? What will be the value when I maximize this expression? Okay. By the way, like you guys should be very careful. Like I have this so many P. Hopefully, I didn't confuse you guys. I have this small P here. It's just the channel crossover probability, but this PX here is the probability of your input distribution, and you have the freedom to adjust that. So some of you guys got HP. That's a little bit weird, actually. I don't know. No. Okay. This is not Gaussian. So we are for this part we are talking about a binary symmetric channel. We start with something simple first. I'm not sure we have time to talk about Gaussian channel, but you mean just this part of like Robert, like your question for? Okay, someone have like the right answer. So maybe let me repeat the whole thing again. So we have this binary symmetric channel have a property that this is basically a channel, right? You have some X coming in, then you have some output Y, right? So it's a binary, so you can have like you can either like send a 0 or send 1 here. And when you send 0, at the output side on the other end of the channel, it can either output a 1 or 0. You can get a 0 or 1. So you have a probability of P that have error, or this crossover probability that like you send out, you send in 0, but like you get 1 instead. And at the same time, like you can have a symmetric crossover probability that like you may send out 1, but with probability P that like you get 0 instead. Now, then the capacity of the channel, I didn't prove it yet, but it's quite intuitive, right? The amount of information you can send through this thing will be just simply IXY, right? The amount of information shared between the two ends of the channel. And so of course you can adjust px here, right? When you for the ixy will depend on both, basically will depend on just the joint distribution pxy, right? But py given x is given by the channel, that's specified by the channel, but px I can control that, right? So therefore, like the capacity will be simply equal to maximizing ixy with respect to px. Now ixy is equal to hy minus hy given x, right? And we said earlier from the earlier question that like hy given x is just equal to hp, and then remaining we will just have like the capacity will be equal to hy minus hp, trying to maximize this over the distribution of p, distribution of x. What I want to say is that I can make what's the maximum hy I can get is like when this is uniform, right? I argue that I can get this uniform if I make x is uniform. So if I have x is equal to have like probability x equal to 1 equal to probability x equal to 0, then I equal to 0.5, then py equal to 1, you can usually show that like will be also equal to 0.5. Right? Because py equal to 1 in this case, what? Maybe I just write it out. Py equal to 1 here, therefore will be just equal to py equal to 1, px equal to 1. Wait a sec. Sorry. X equal to 1, px equal to 1, right? Plus py equal to 1, x equal to 0, px equal to 0, right? So what I'm doing here is like nothing, but it's just base rule and then marginalize out x basically, right? But this guy here is equal to 1 minus p, right? And this guy here is equal to p, right? And x equal to 1, let's say 0.5 and 0.5, right? X equal to 1, and both of them are uniform, or like x is uniform, both x equal to 1 and x equal to 0 is equal to 0.5. Then this which is just equal to 0.5 p plus 1 minus p, right? So therefore just equal to 0.5. So if I have x is uniform, then y will be uniform as well. Like, so y is uniform, then hy will be just equal to 1, right? So therefore, like, and I cannot get like more than 1 base. The maximum is 1 base. And I know I can achieve that by making like px is uniform. Therefore, like the maximum hy is just equal to 1. So therefore, like this will be just equal to 1 minus hp. Yeah. And let me do this. Instead of use p, I need the crossover probability called q then. Like, let's see, this is all q here, and then this is hq here, this is q here, basically. Yeah, and this is a probability of px. So yeah. Yeah, something like that. That's maybe some q here, yeah. So I guess this is about to. So I guess I will come back to talk about Gaussian Gaussian channel like next time when we are back with all the presentations. And let's see. Anything else? I think. Yeah. So okay, I guess okay. I guess I will I'm kind of like eager to listen you guys presentation. Okay, don't forget to submit your presentation abstract today. So and then I will see you guys next week then. Okay, bye. Yes.